Everybody, welcome back to Tech Junior Tutorials. My name is Lee Warwick Jr. and this is Advent of Code. So today's actually day 15, but I'm going to be talking about day 14 because it took me forever to get this one. This one was super tough, and I felt very discouraged doing this one. I definitely felt like I had hit my limit on brain power for this. So also, I think I'm coming down with a cold, so forgive me if I sound a little nasally, but let's check out this puzzle. So day 14 is space stoichiometry. If you don't know what stoichiometry is, it is a high school chemistry kind of thing where you're balancing reactions. So you have a certain amount of elements on one side, a certain amount on the other side, and you need to balance to find whatever answer you're looking for. So they say you're trying to find some resources to turn into fuel. So they give you this little equation. They say like, okay, if you get 10 ore, that creates 10 of A. So the letters are elements, and you need to find out the minimum amount of ore required to produce 1 unit of fuel. So basically, you would look at this and say like, okay, 1 fuel costs 7 of A. 7 of A is going to require at least 10 ore. So you get 10 of A. So here's where the rub on this problem is. Like, if you look at the example here, you're just walking backwards, and it's a 1-to-1 for pretty much everything. And so 1B is 1 ore. So 1 of E is just 1 ore. But for the A, this is going to cost, so 7 for the initial, 7 for reaction with E, 7 for D, 7 for C. So you would think that this would be, I don't even know. They give you an example here that's like 7 plus 7 plus 7 plus 7 is 28, but then the answer that they're looking for this one is 31. So 1 ore to produce 1 of B, and 30 to produce the 7 or the 28 A's that are required. And so that is because of you can only get 10 at a time at a minimum. So you would get 30 of A right off the bat. And then the 1, excuse me, the 1 comes from the 1B from walking backwards. So as you can see, this one's already getting pretty complicated. The examples only get more complicated from there. So for this one, a little bit bigger of an example, but they kind of break it all down, which is kind of nice. So they say like, you've got to, and they do this one forwards to backwards, but to get 1 fuel, you need 2 of AB. So 2 of AB costs 6 of A and 8 of B. 3 of BC is going to be 15 and 21. 4 of CA is 16 and 4. And then when you add all those up, you get 6 and 4 is 10. If you add the B together, it's a run away from me. 8 and 15 is actually 23. But they say you have to get 24 because if you look up here, you can only get B in increments of 3. So you can't get 23, you have to get 24. And then C is 40. So 21 and 16, which again is less than 40, but because you can only get increments of 5, you have to get 40. So basically what they don't really explicitly say is that when you're getting all of these elements, you've got some extra ones. So it says up here somewhere, 2 extra A wasted. But they don't tell you that whenever you waste those elements, that those are supposed to be like free floating in the reaction pool to be used for any other reactions. So basically you don't see this in the first couple examples. So this one is like pretty straight up. There's no reused chemicals that you need to worry about. Same thing with this example. Same thing, sadly, with this one, at least from what I saw. But when you get down to this example, all of a sudden, like, I had done the problem where I was walking backwards through these reactions from like bottom to top and just getting the total amount. So I got that right away. I got this 165 right away. I got the 31 right away. But when I got to here, I got like 182,000. So I was thinking, man, I must have a rounding error somewhere that just popped up when I had a bigger group of numbers or something to that effect. And then I tried this one and I got like 200 and I'm sorry, this is 2 million. So I got like 2,220,000 or something like that. And I was like, So the order of magnitude is bigger for the bigger set of numbers for my overages. So I really thought that I had a rounding error, but that wasn't the case. It was that I was not using the spare elements properly. And so basically I haven't had a whole lot of time to sit down and do this until tonight, where I had a couple of solid hours to sit down and concentrate. And so I wrote this solution that was like absolutely insane. It was hundreds of lines of like Python dictionaries and stuff, and I was trying to do like wacky amounts of recursion, and passing elements down and up and extra elements and creating extra elements and all kinds of madness. So let's check out what I finally landed on. So here is my solution. Most of this is example code. So I copied over all the examples, but I had to reach out for help for somebody to help me understand what the problem was with my original solution. And what they gave me was this. So if you look at this example, this one is small enough that it shows you what to do with the reuse elements. So you would think with this one, going off the instructions, like I need 5 of A, so that's 5 right off the bat. 1 of B, which is going to be 20 ore because A is 1-to-1. And then 1 of C, which is going to be another 10, and then another 10, so 35. The answer is actually 25 for this one. So basically, do the 5A, that's pretty much done. You do the 1B, and when you do 1B, that gives you 2, because the minimum amount of B's that you can make is 2. So you get 1 extra B. And then when you do the 1C, you don't have to calculate that 1B or take that into account. So that is like one element that you don't have to worry about, basically. You only have to calculate the 10A. So that means 5, 10, and then another 10 here for 25. And that was just blew my mind. Trying to apply that to the other examples, I was, like I said, I was passing stuff up and down and all over the place. But yeah, if we look at this, you can see I get 25 here. So I finally was able to figure that out. So we can run some of these other ones just to see. So there's the one that says 31. Again, that one doesn't really take into account extra elements, but example 4 definitely does. So there's the 180,697. And then the the final answer for me was 431,448, which if we scroll down, you can see here. So what I had to do for this was kind of maddening, but first what I did was I basically stored everything as a dictionary, and what I did was I flipped all of these elements. So I said, like, here's my here's all my reactions, right? So I'm going to look and say like, okay, a fuel has a formula that's Ca, Bc, and Ab. The minimum amount of fuels that I can make is 1. And then for the Ca, it requires 4, and Bc requires 3, and so on. So basically, split based off of that fat arrow, and then split again the molecules themselves by a space. Or I'm sorry, I split the original thing, so like 1 fuel, I split that by a space. And then for all of the elements, I split those by comma space. Excuse me. So after that, store all that in a dictionary, and we can see that. Well, let me use one of the smaller ones. So you can see, like, here's my fuel, and then here is my minimum amount, and then the formula, and then that's just another dictionary of items. So that made things a little bit easier to work with. I kind of got used to this trick from doing the orbital problem from a few days back, I think day 6. So that was actually last week, but walking down that dictionary structure was not that bad. So from there, what I had before was like what amounted to one giant function, and then I broke it up into like 3 functions. It was kind of crazy. So here I have a get cost and the extra. So I look at the minimum amount. So like let's say I want 1 of A or something, and that produces 10 of A as a minimum. So like the minimum would be that. And then I calculate like how many times do I have to run this to get that minimum amount. And so I do a math.ceil. So I round up the amount divided by the minimum amount. So if I need 1 and I'm going to produce 10, that's still going to give me 1. If I need 2 and the minimum amount is 1, that'll give me 2. If I need 3 and the minimum amount is 2, that should give me 2 when I round up. So then I say like my final amount is going to be times run times minimum amount. And then I say, hey, if the final amount is bigger than the amount that I originally asked for, go ahead and say like that the extra is that difference. Otherwise, the extra is 0. And then for my cost, I go through that list of things in the dictionary. So I go through this, A, B, and C. And I grab the ingredient times the amount of times that I'm going to run this thing. And then I return that cost and however many extra I just created. So that's definitely the simpler of the two. My reduce function, probably a poor poor naming of function. I think I overwrote the built-in reduce function, so I should call that like reduce formula or something. Let's see if my still going there, so that's good. So for this function, right off the bat, I call my previous function and just like, okay, give me the cost of this. So if you look through the examples and through the input, they were nice enough to give you a fuel formula that always produces 1 fuel instead of like 2 fuel or 3 fuel or whatever. So that reduced the complexity a little bit. So I use this underscore to just say like, don't worry about the extras, basically. So from there, start a counter for total ore, start a dictionary for extra molecules that I'm going to have, and then I just do a while loop. So before I was doing this recursively, and that was blowing my mind. I was recursively getting like all these elements and the extras and stuff. It was too much to keep track of. I was making the problem a lot harder than it needed to be. So this way, I just get the extras kind of at each step and then break out of what I'm doing. So Remember the cost is going to be a dictionary. So for each element in the cost, I'm going to say like, hey, if that thing is in my extras, and this is a lot of complicated code, but if basically get the difference of that, and if I've got more of that thing in extras than I need, go ahead and pull that out of my extras and then delete the cost and then break out of my for loop here. Because like I don't even need to calculate it. Like I've already basically accounted for it in my extras. Otherwise, reduce that cost by the amount extra that I have and then delete that thing from the extras dictionary. Otherwise, like they must be equal, so they've canceled each other out. Delete both and then break out of this for loop. Then if I've got an element that is converted directly to or from that is, do the same thing, get the cost, which is and however many extra. And then I say, if I've got extra, go ahead and add that to the extras array or dictionary. And then delete the cost. So like if I've got 10A in this other example, or actually, let's see. Yeah. So let's say I needed 10 of A. It's like, okay, that's going to cost you 10 ore. Go ahead and not worry about that from that point because that's done. Once you say, so let's say it was 7A. For this top level example, I would say like, all right, that thing comes directly from ore. So plug in 7 here. That means I'm going to get 3 extra. Go ahead and delete this from my my costs, and go ahead and add 10 ore to my ore counter, and then add the 3 extra to extras. So I got 3 extra A's flying around. And then I break if I've deleted cost because that is going to change the size of this dictionary. So that just kicks it back off again because it's in a while loop. Otherwise, go ahead and get the cost and the extras, delete the cost, do the same thing with the extras, add them to that dictionary, and then for the ingredient in the costs, just add those to my costs array. And then if I've finally depleted everything in the costs, that means I've converted everything in the costs dictionary. I said array before, excuse me, dictionary. If all the costs are gone, so the dictionary is of size 0, switch running to false and return the total ore. I probably could have returned total ore here instead of doing running false or whatever. Let's see if I can do that. Sorry, I just I basically just solved this, and it was a real animal. Yeah. So that's basically it for that one. Yeah, I should really. I'm gonna copy this over to delete these. You can see this is like a really long, confusing function. I don't know what that is, like almost 50 lines. So not really super proud of that, but it kind of does the job. Let me port this over to part 2. So for part 2 of this, now they say you've got 1 trillion units of ore. So you've like gone nuts and just let that thing run for a while, I guess. And they want to know, okay, you've let this thing run, you've collected a bunch of ore. How much fuel can you actually produce from this? So originally I thought, okay, maybe they want me to like produce 1 unit of fuel at a time, see how many extra elements that I have left over, produce another element of fuel. And so I did like a for loop, or actually a while loop until I had hit the amount of fuel, I believe. Uh, anyway, I compared these numbers and ended up overshooting this by quite a bit, by like 20,000 or something with that method. And so I realized that they're trying to get you to guess basically this number to produce or to get as close to a cost of 1 trillion units of ore without going over, and then seeing what that maximum fuel value is. So doing that, there's like a dumb way, which is what I tried at first, and then the really hard way, which is with an algorithm basically. But I don't think I've kept the silly way in here. Yeah, I did not. So again, this reduce formula thing is the same as part one. Essentially, for part two, you need to know how much fuel it costs, or how much fuel you would produce to go over 1 trillion units, and then some amount lower than that, and then guess. Basically, do like a binary search to get in between there. At least I think that's what it is. But what I did at first was basically count up from 1 fuel and be like, okay, what about 2 fuel? What about 3 fuel? What about 4 fuel? And so this one, doing that never finished because it produces so little fuel per increment. So it took forever to count up this high. This one actually did finish that using that stupid method, but it took a good 10, 15, 20 seconds or something like that. And then for the actual puzzle input down here, it never finished. So that was a no-go. So I had to do the harder way, which is basically first I needed to go over that amount. So to do that, I just said like, while I'm still undershooting the ore cost or the collected ore, go ahead and double the fuel amount. So start at 1 and just double it and keep doubling it until I go over. And then once I go over, it's like, okay, here's my lower limit, here's my upper limit. So my lower limit would be the last fuel amount before I doubled it. And then the upper limit is going to be that current fuel amount. So I know it's between those two numbers, basically. And then from there, I do this guess fuel split. And so what that does is it says, okay, here, I'm just passing down that 1 trillion ore, by the way, in here. So I pass down the 1 trillion and I say, okay, here's your lower, here's your upper. Find the middle number between those two. And so I take the upper minus the lower, divide that by 2 and round down, and then add that to the lower, so that if I had like a lower of 500 and an upper of 1,000, the difference of those is 500, divided by 2 is 250, plus the lower of 500 is 750, and 750 is directly between 500 and 1,000. So from there, then I say, okay, if you've overshot it again, yeah, if the cost is greater than the limit. So if you've overshot it, don't look at the upper half, look at the lower half. So look between lower and the middle number. Otherwise, and I got into trouble here again, otherwise, basically look at the upper half. But what I was missing was this was running forever because I was going above and then going below and going above and going below. And it was never that perfect number. So what I did to fix that was basically what happened is I basically ran it and then hit Control C to stop the program and saw that I was recursively calling the answer over and over again. So basically I said like, hey, look at the middle plus 1. And if that is overshooting it, then you've hit the number. Otherwise, like, go ahead and split it again. And so doing that, you can see like when you run the puzzle input, here's the lower that it eventually started with, and there's the upper. So basically doing that magnitude of 2 and doubling the fuel cost until I get over and under, and then basically split those right down the middle and kind of recursively find the thing in the middle. So that runs, you can see, like super fast. That's a way more efficient way of doing it than counting up by 1. It's pretty much instant even for this input, which should take a long time. The example 3, which is this one. So you can see like it was able to find that number 82 million like really fast. So again, that's why like there's a lot of value in these sorry, I'm I'm so like tired and feeling sick, but there's so much value in these advent of code problems because they make you realize like how efficient your code is. So yeah, you can get it done the dumb way and just count up, which will work most of the time. And speaking as somebody that's like a newer developer and a JavaScript person, and a lot of the stuff in front end is not crunching heavy numbers. It's just, hey, I need the number, and processing speed and memory and stuff is at an all-time low as far as cost. So go ahead and do it. Just crunch the numbers and do the stupid algorithm, and you get the answer, and nobody really notices because the processing time is on magnitudes of like milliseconds, right? So to the human, it's imperceptible. But when you're running these advent of code problems and you're actually looking for a number in the trillions or something, and doing lots of calculations and computations while you're looking, it does matter. It matters a whole lot. And so you can definitely slow down your computer and make everything chug and never actually get the answer and just let it run and run and run and run out of memory. So that's really cool, and it's interesting to work on problems like that because you don't really get to see those day to day and while you're programming. So I know that day 15 is a pathfinding maze problem. I don't know if I'll be able to get to that one anytime soon. Got some busy days coming up. Plus I've come down with some kind of cold, so we'll see how fast I can get to it, and if I can keep going with these. If any more of these are like today's, I don't know how many more of them I can fit into my my schedule with the holidays. But I was really happy that I finally got this one because this one was a beast. If you didn't get this one, don't beat yourself up. Even the smartest people that I've been talking to that are doing this with me, it really hammered them too. So don't beat yourself up over it. All right, that's all I've got for this one. I will talk to you later.